Hey growers, welcome back to the castle. It's time to drop some more science on you. So let's pick up where we left off last week in true Scottish style. Let's pick up where we left off last time. And see what this week's subject is. Today we're going to look at a subject that is all too often overlooked by most growers, and that's what PPMs are and how do we calculate the PPM levels that we're delivering to our plants when we make up a nutrient solution. Today we're going to look at how to do that with dry fertilizer products. You might ask why this is so important. Well, we know that plants need light, water, and nutrients to grow and thrive. If they're growing outdoors, they'll get all of the nutrients they need from a nice rich soil. But when they're grown inside, they need to get all of their nutrients from us. And remember from my previous videos that fertilizers need to be comprehensive, meaning they contain all the macro, secondary, and micronutrients needed. And they have to be balanced, meaning that the nutrients must be in the proper ratio to each other. Fertilizers that are not balanced are apt to cause what are known as induced deficiency. That's where the nutrient components that are in excess act by actually impeding the uptake of other nutrients in the solution. So let's take a little closer look at this. As commercial growers, we need to follow very strict nutrient recipes when we're feeding our plants. If we don't, we're apt to have suboptimal growth, which will translate to poor quality and a loss of both time and money. So when we start to look at how to feed our plants in a commercial operation, we go by some very strict recipes. This is one from the University of Tennessee showing a very commonly used fertilizer recipe in the commercial world. This is called the Steiner solution. It acts as a base, and then we will modify it according to the specific plants and life stages that we're growing. But you can see from this that it's not simply throw a little bit of nitrogen in and then a handful of calcium and a pinch of boron and then a half a cup of phosphorus. It's very precise. These readings are all in PPMs or parts per million. 171 parts per million in nitrogen, 48 of phosphorus, and on down the line. This is important to floriculture growers and food production growers, and also to those of you who are in the high-value medicinal world. The team from University of North Carolina of Brian Whipker, Jim Smith, Paul Coxon, and Hunter Landis do a lot of research on optimal conditions and nutrient solutions for the medicinal sector. This is one of their little charts that will give you an idea of how precise nitrogen application is to a successful medicinal crop. Early veg, the desired target is 100 to 125 parts per million. Peak flowering, 200 to 225 parts per million. Back down to 100 and 150 parts per million in pre-harvest. It's that precise. When we look at this whole concept of induced deficiency, here's an excerpt from an article from a Penn State Extension Service bulletin. The important part here is that when one nutrient is in excess, it can be taken up at a higher amount at the expense of another nutrient. This is nutrient antagonism. In this case, it is possible to have sufficient amounts of a nutrient in the nutrient solution and for the plants to be deficient. On the right, we can see another chart from Brian Whipker and his crew looking at what this might mean to us as growers. Excess nitrogen can potentially cause a deficiency of potassium and calcium, even though the potassium and calcium levels are proper within the nutrient solution. Calcium being in excess can cause deficiencies of magnesium and boron. I see a lot of signs of calcium and magnesium deficiencies in the commercial grows that I spend time in. And very often it's not due to the fact that there isn't enough calcium and magnesium in the nutrient solution. It's that some of the other nutrients are in excess and they're causing this induced deficiency. So what's this mean to us so far? Before we proceed, let's just look at a little bit of a review here. We know what plants need from decades of research. We know we need a fertilizer to be complete and to be balanced. Producing that complete balanced fertilizer takes a lot of precision and a lot of data, and that's what we pay manufacturers to do. We should trust them. If they're following the science, the product that they make for us should meet all of the data requirements for that plant. When we try to make our own fertilizer or follow a buddy's advice, that's when we can get into trouble. Put a little bit of this in, a little more of that, take a product from this line, add it with a product to that line. The PPMs and the balance get completely out of whack and our plants suffer for it. You've heard me say this many times, and I'm going to say it again here. Whenever you add anything to your soil or nutrient solution that's not listed on your manufacturer's feed schedule, you should have a good data-based reason for doing so. In other words, why are you putting it in the first place? So where do we go from here? As commercial growers, it's our job to be familiar with the current data relating to the optimal nutrient requirements for the plants we were growing and the life stage that those plants are in. We want to make sure that we choose a fertilizer that's based on that latest data, and that we're choosing a fertilizer meant to be used for the plants we are growing. We don't want to use a lettuce-specific fertilizer to grow tomatoes or tomato-specific fertilizer to grow corn. We have to know that the fertilizer we choose is appropriate for the crop that we're producing. Make sure you understand and follow the product's feed schedule. Here's a big one that I talk over and over and over about. Use an EC meter to accurately measure your input level of fertilizer and do periodic outflow testing of the EC. I cannot emphasize the importance of this. And if you have questions, you can watch my video on EC meters and fertilizer chemistry. Have your water tested to assure the compatibility of your chosen fertilizer with the chemistry of your water. I did a video recently explaining the importance of this, and I can't emphasize how many people get into trouble when they do not have their water tested and match their fertilizer to that water. And again, don't add more ingredients to a nutrient solution without a good reason. So now on to the meat and potatoes of this video. What is a PPM and how do we calculate what level of PPMs we're giving to my plant when we make a nutrient mix-up? We'll look at a little paragraph here by Nell Matson from Cornell University. The basic principle we follow is that 1 ppm equals 1 milligram per liter. This is based on an inherent property of physics, and this is the key to everything we're going to talk about here. 1 liter of water at room temperature weighs 1 kilogram. I'll repeat that. 1 liter of water at room temperature weighs 1 kilogram. And remember, 1 kilogram equals 1,000 grams. 1 gram equals 1,000 milligrams. So 1 kilogram equals 1 million milligrams, because there's 1 gram equals 1,000 milligrams, 1,000 grams equals 1 kilogram, so that's 1,000 times 1,000 equals a million, so 1 kilogram equals 1 million milligrams. So if we take 1 milligram of, say, nitrogen, put it into a liter of water, we're putting 1 milligram into 1 million milligrams of water, so that 1 milligram of nitrogen we put in is going to be 1 part per million. It's 1 milligram of nitrogen in 1 million milligrams of water. So that's where we get this 1 part per million. When you look at a research paper or some of the higher end fertilizer company bags will even write it this way, you will see 1 ppm, which means 1 part per million, equals 1 milligram of that nutrient component per liter of water. It's written in scientific notation as 1 mg. The slash will mean in or per, and the L is liter. So 1 ppm is written 1 mg/L, 1 milligram per liter. If we look at that 1 milligram of nitrogen we put into that liter of water, that would be written 1 mg, 1 milligram/L per liter, and the N of nitrogen. So 1 part per million nitrogen is written as 1 milligram / being per liter of nitrogen. Easy for you now. We're going to take a step and actually do a little bit of calculation and how you can use this as a critical tool in your grow operation. So it's time for you to buy some fertilizer. And from your research and from the type of plant that you're growing, you know that for the life stage that your plants are in, you want to be delivering somewhere in that 200 parts per million of nitrogen when you feed. So you go out and you start looking at dry fertilizers, and they can be products like Jax or Psycho, General Hydroponics, Athena, or any of them. And you pick a bag up, and the 3 numbers on the front of the bag might say something like 15, 5, 20. They can be any combination of numbers. We're just taking this for example. That 15, 5, 20 means 15% of the weight of that product is nitrogen. The first number is always nitrogen. The second is phosphorus. So 5 on the bag means that 5% of the weight of that product is phosphorus. The 20 is for potassium, and it means that 20% of the weight of that product is potassium. And remember, these numbers can be in any combination. We're just taking the 15, 5, 20 as an example. So, how much do we add to our gallon of water to get that 200 parts per million delivery rate? First, remember that all of this ppm information is based on that basic concept that 1 liter of water weighs 1 kilogram. 1 liter of water weighs 1 kilogram, which is 1 million milligrams. So the only formula that we need to use to understand this is this formula here. First, we want to divide the target ppm rate that we want to reach. In this case, we want to reach 200 parts per million. So divide the target ppm rate we want to reach, which will be 200, by the percent of the element in the fertilizer that we're trying to calculate. In this case, it's nitrogen. And we look at what the percentage of the element is. In this case, we're doing nitrogen, it's 15%. So when we look at what we're calculating, we're taking 200, which is our target ppm, divided by the percent of the element. And when we divide by the percent, if it's 15%, we move the decimal point 2 places to the left. So we've got 200 divided by 0.15, that's the 15%. And the result of that gives us 1,333.33 milligrams. That means that we're going to add 1,333.33 milligrams to 1 liter of water, and that's going to give us 200 parts per million of nitrogen in that liter of water. But we don't normally deal with milligrams. We normally will deal with grams. We know that a milligram is 1,000th of a gram. So to convert that 1,333.33 milligrams to grams, we just divide it by 1,000, which gives us 1.3 grams. So we've just calculated that if we have a liter of water, we add 1.3 grams of our 15,520 fertilizer, and that will give us a ppm of 200 parts per million. But again, we normally don't calculate our solutions in liters. We use gallons. So we just do a very simple conversion here. 1 gallon of water equals 3.785 liters. So if we're putting 1.3 grams per liter and a gallon is 3.785 liters, all we need to do is multiply 1.3 grams per liter times 3.785, and we get 4.92 grams per gallon. So that was pretty easy. We now know to get a nitrogen ppm level of 200, we would need to add 4.92 grams, and it's easier just to say 5, of our chosen fertilizer, being the 15,520, into 1 gallon of water, and that's going to give us 200 parts per million nitrogen for our nutrient solution. And conveniently, 5 grams equals 1 teaspoon. So we've made our mix-up originally now based on how much we put in of our fertilizer to get to 200 parts per million nitrogen. But when we put that fertilizer in, we're also putting all of the other elements in, the phosphorus, the potassium, the calcium, and the magnesium. But we have to figure that on the amount that we put in already to get to the 200 parts per million of nitrogen. So let's look at an example of another element and see what that translates to as parts per million when we add the 5 grams to reach the 200 parts per million of nitrogen. So let's look at phosphorus as an example. We know from research that phosphorus levels for medicinal crops would like to be somewhere in that 60-70 parts per million from the current research data. When we look at our formula for figuring all of this information, on the right side of the equation, we already have put in that 1,333.33 milligrams per liter when we made up our solution to get to 200 parts per million nitrogen. So this is fixed. On the left side of the equation, we know that we're calculating now for phosphorus, and the percentage of phosphorus is 5%. So we're dividing by 5%, or 0.05. The variable that is unknown yet is the ppm of phosphorus. That's the X, the unknown at the moment. So the equation would be X, which is the unknown phosphorus ppm level to date, divided by 5%, and that's going to equal the 133.33 0.33 milligrams per liter, but we want to equalize, balance this equation and just solve for the x. So we do simple algebraics and multiply both sides by 0.05, so we just have x on the left to solve for. So now we have x equals 0.05 times 1,333.33 milligrams, and that gives us 66.66 parts per million of phosphorus. And we can go right down the line and do that for any of the other nutrients, but we can see that this 15-5-20 fertilizer mix, when we make it up at 5 grams or 1 teaspoon per gallon, it gives us exactly what we want for the 200 parts per million of nitrogen, but it also gives us the exact levels of phosphorus that we're looking at. And if we went down the line and looked at the other nutrient elements, we'd find that they were right in line with where current data tells us we want to be for our nutrient level inputs. That means that the manufacturer has used science to produce a product that is exactly specific to the plants we're growing and the stage that those plants are in. And just for your information, the product I used for these calculations was the JAX 15-5-20. This is very critical if we're going to be precision growers. All right, that calculation went so well, I think it's probably time that we even push the envelope a little further. Let's take another example here that we look at your fertilizer and see that it's a bit low in magnesium. And when we look at your water test results, that also shows that your water is quite low in magnesium. So your plants are starting to show some interveinal chlorosis, and we know that you need to add a little more magnesium. So you talk with your science resource, and you come to the conclusion that you should add some Epsom salts to give an extra boost of magnesium, probably in the level of, say, 40 parts per million. So how much Epsom salt do you need to add per gallon of water to give you that extra 40 parts per million magnesium boost? We use the same equation. You take your target ppm, which is going to be 40, divided by the percent of the nutrient that we're trying to calculate, the magnesium, and that gives us the milligrams to add to 1 liter of water. So Epsom salt, or magnesium sulfate, is 9.7% magnesium and 13% sulfur. So our calculation will be 40, the target ppm we're trying to reach, divided by 0.097, the percent of magnesium in the Epsom salt, and that gives us 412 milligrams per liter. We know we want to convert to grams, so we divide that by 1,000, so it gives us 0.4 grams per liter. And remember, a gallon is 3.785 liters, so we multiply 0.4 times 3.785, and we get 1.5 grams per gallon. Remember, a teaspoon is 5 grams, so this isn't very much Epsom salt. It's about a quarter of a teaspoon per gallon. But now, because Epsom salt is magnesium sulfate, you might want to know how much sulfur we're actually adding. And sulfur is an important element when we start talking things like flavor and odor. So how much sulfur does this contribute to our nutrient mix? All we have to do is multiply the total milligrams per liter of magnesium sulfate, or Epsom salt, that we added, and that's 412 milligrams per liter. We multiply that by the percentage of sulfur in the Epsom salt, which is 13. So we just have 412 times 0.13, and we're adding 53.56 milligrams per liter of sulfur, or if you remember from our notation, the mg per liter is actually the ppm, so we're adding 53.56 parts per million of sulfur in addition to the 40 milligrams of magnesium. Phew. Okay. So the takeaway of all of this math and calculations that we've done, first, the most important thing is that successful growing is precision growing. The window to optimal growing is quite small. There's a lot of things that have to be in correct balance for you to reach that optimal level. It includes everything from lighting spectrum, lighting intensity, temperature, vapor pressure deficit, ventilation, nutrient management, hydration, water content of the soil, but nutrient availability and ppm delivery is a critical part of successful growing. And if we don't pay attention to all of these set points within our grow area, what it will do is we'll have suboptimal growth, suboptimal quality, and we're going to be wasting time and wasting money. And again, whenever we add inputs that are not called for by data or called for by the feed schedule from the manufacturer, we run the great risk of seeing induced deficiencies or toxicities. I highlight this because it is so important. PPMs, just like EC readings, are a science and data-driven tool to help you realize your best harvest and help assure your business success. Large growers, large commercial growers, take this very seriously, and you should take it seriously too. The data is there. The science has shown us what plants need, when they need it, the exact levels. If we're not following the science and the data, we're doing nothing but impeding our ability to be successful in the business. We're cutting down on the productivity and we're cutting down on quality. So understanding PPMs and how to calculate and manipulate them is critically important in your business. In part 2, I'm going to look at how to calculate ppm levels when you're using liquid fertilizers. So until next time, remember, you need to know what your plants need to grow.